326 years. That is how long the Cascadia subduction zone has been silent. The last time it moved, it generated a magnitude 9 earthquake and sent a wall of water across the Pacific Ocean that reached the shores of Japan 10 hours later. Japanese records from January 1700 describe a mysterious tsunami that arrived without any local tremor to explain it. Centuries later, geologists connected those records to the Pacific Northwest. And right now, in the spring of 2026, a cluster of new studies is quietly changing everything we thought we knew about that silence. Write in the comments where you are watching from, and we continue. In February this year, a research team from the University of Washington published findings from the first ever offshore strain monitoring of the Cascadia Fault. They deployed instruments at 3 sites along the subduction zone between 2017 and 2022, measuring seismic velocity changes deep beneath the seafloor. What they found was not simple. The fault is not behaving as a single, uniformly locked boundary. Different segments are showing different dynamics. Some areas appear tightly locked, accumulating pressure with no release. Other areas show signs of fluid migration through perpendicular faults, which could alter how a future rupture propagates. The lead researcher, doctoral student Malene Kittiwela, put it carefully. The evidence suggests the fault is not completely locked everywhere. But where it is locked, the strain is building. That study alone would be enough to merit attention, but it did not arrive in isolation. 1 month later, in March, a separate team led by geologist Brandon Shuck published results from the KC-21 expedition in the journal Science Advances. Using deep seismic reflection imaging, they mapped a tear in the Juan de Fuca plate roughly 30 to 130 kilometers off the coast of Vancouver Island. The plate, which has been subducting beneath North America for millions of years, is not intact. It is fragmenting. A section called the Explorer microplate is peeling away from the main body of the Juan de Fuca plate. The tear is approximately 35 kilometers long and runs parallel to the trench. Headlines briefly celebrated the idea that Cascadia might be shutting down, that the subduction zone could be losing its ability to generate megaquakes. But within weeks, multiple analyses from McMaster University, The Conversation, and others made it clear. The interpretation had run ahead of the science. The plate boundary is not winding down. It is becoming structurally more complex. And structural complexity in a subduction zone does not reduce risk. It redistributes it. It means that instead of one predictable system, scientists are now looking at a segmented, fractured boundary where different sections may behave independently, each with its own stress profile, its own locking characteristics, its own potential for rupture. That distinction matters more than most people realize, and to understand why, we need to look at what is happening beneath the seafloor right now, in places where most monitoring stations cannot reach. The complexity beneath the seafloor is real, but the problem is not just what scientists are finding, it is how little they have been able to see until now. The Cascadia subduction zone stretches more than 1,000 kilometers along the Pacific coast, from Northern California through Oregon and Washington to southern British Columbia. It marks the boundary where the Juan de Fuca plate, a remnant of the ancient Farallon plate, is being forced beneath the North American plate at a rate of approximately 4 centimeters per year. That rate sounds negligible? It is not. 4 centimeters per year, sustained over 326 years of silence, translates to roughly 13 meters of accumulated displacement. 13 meters of stored elastic energy along a fault that, when it last released, moved the coastline by several meters in a single event and dropped entire sections of shoreline below sea level permanently. What makes Cascadia uniquely difficult to study is that the locked zone, the area where strain accumulates before a megathrust rupture, lies entirely offshore. Most seismic networks in the region are land-based. They can detect earthquakes once they happen, but they cannot directly measure the slow, silent processes occurring on the fault interface beneath the ocean. This is the equivalent of trying to monitor a patient's heart condition by listening through a wall. You might catch the cardiac arrest, but you will miss every warning sign that preceded it. This is precisely the gap that the COS-ZO project, funded by a $10.6 million grant from the National Science Foundation in 2023, is designed to close. Scientists and engineers from the University of Washington, working with partners at Scripps Institution of Oceanography, are building an underwater observatory directly on the Cascadia subduction zone. The instruments will sit on the seafloor at depths ranging from 75 to over 1,000 meters, connected to shore by fiber optic cable through the existing Ocean Observatories Initiative infrastructure. Seismometers encased in titanium spheres will be buried inside steel pipes driven into the sediment, suspended on glass beads so they float without touching the pipe walls, a design engineered to eliminate noise and capture the faintest signals from the fault below. The pressure gauges are equally precise. They are designed to detect vertical movement of the seafloor as small as 1 millimeter per year in 1,000 meters of water. That level of sensitivity is what it takes to catch the kind of slow slip events and subtle deformation that may precede a major rupture. The first instruments were scheduled for deployment by summer of 2026. That means the window of direct offshore observation is only now beginning to open. And this is the part that should give anyone pause. For over 3 centuries, the most seismically hazardous subduction zone in North America has been accumulating stress in a place where no instrument could measure it in real time. Every probabilistic assessment, every hazard model, every risk calculation has been built on indirect data, historical proxies, and land-based extrapolations. The question is not whether the data was wrong. The question is whether it was ever complete enough to tell us what we actually need to know. The data may not be complete, but what exists in the geological record is enough to establish one thing with certainty. Cascadia has done this before, and it has done it repeatedly. The modern understanding of Cascadia's seismic history began not with instruments, but with buried trees. Along the coasts of Oregon and Washington, researchers in the late 1980s discovered entire forests of ancient Sitka spruce and western red cedar preserved beneath tidal marshes. These trees had not fallen, they had been drowned. Their root systems sat in soil layers that had suddenly dropped below sea level, evidence of massive, instantaneous land subsidence consistent with a megathrust earthquake. Radiocarbon dating placed the event around 1700. But the precision came from an unexpected source. Japanese historical archives documenting a tsunami that struck the coast of Honshu on January 27, 1700, with no corresponding local earthquake. Working backward from tsunami travel times across the Pacific, geophysicist Kenji Satake and his colleagues narrowed the origin to Cascadia and calculated the time, approximately 9 p.m. local time on January 26th, a magnitude 9 event. The entire fault, from Vancouver Island to Northern California, rupturing in a single coordinated release. That was the most recent event. It was not the only one. Seafloor sediment cores extracted from submarine channels off the Pacific Northwest coast contain layers of turbidites, deposits of sand and silt that settle after being shaken loose by strong ground motion. By counting and dating these layers, researchers have identified at least 41 full margin ruptures over the past 10,000 years. The average recurrence interval is approximately 243 years for events that rupture the entire zone. But the data also shows shorter intervals of partial ruptures affecting only the southern segments, with return periods as brief as 170 to 220 years in some sections. The 326-year gap since the last full rupture exceeds the average by more than 80 years. This is where probability enters the conversation. The United States Geological Survey and Oregon Department of Emergency Management currently estimate a 37% chance of a megathrust earthquake of magnitude 7.1 or greater along the Cascadia subduction zone within the next 50 years. A separate United States Geological Survey fact sheet from September 2025 places the probability of a full magnitude 9 rupture at 10 to 15% in the same time frame. These numbers sound moderate until you compare them to other hazards. A 37% probability over 50 years is roughly equivalent to the odds of flipping a coin and getting heads twice in a row. Most people would not board a plane with those odds of mechanical failure. But probability models depend on assumptions, and the core assumption behind Cascadia's hazard models has been that the fault behaves as a relatively uniform system. The February 2026 study from the University of Washington challenges that directly. If the fault is segmented, if fluid pathways vary from section to section, if locking is not uniform, then the recurrence models built on a single average interval may be masking a more complicated and potentially more urgent reality beneath them. The recurrence models may need revision. But while that scientific debate continues in journals, something else is happening on a much more practical level, and it is happening fast. Across the western United States, the infrastructure of earthquake preparedness is being expanded at a pace that has no precedent in the last 2 decades. Not with fanfare, not with press conferences. Through budget lines, engineering contracts, and sensor deployments that most of the public will never hear about. In March 2026, a bipartisan group of United States Congress members sent a letter requesting $32.6 million for Shake Alert in the fiscal year 2027 budget. The earthquake early warning system operated by the United States Geological Survey that covers California, Oregon, and Washington. The system, which became publicly operational in California in 2019, detects seismic waves radiating from an earthquake's epicenter and sends alerts to more than 50 million residents in the coverage zone, potentially giving them seconds to tens of seconds of warning before strong shaking arrives. In Washington and Oregon, that window could stretch to a few minutes for events originating offshore. The system has already proven its reliability. Between October 2019 and September 2023, Shake Alert generated alerts for 95 events above magnitude 4.5, of which 94 were confirmed real earthquakes. But Shake Alert was designed with a known limitation. Its original sensor network relied exclusively on seismometers, which measure ground shaking. For the largest earthquakes, precisely the ones that matter most, seismometers can saturate. They underestimate magnitude because the shaking exceeds what the instruments can differentiate. In August 2024, the United States Geological Survey and its partner EarthScope announced a critical upgrade: the integration of Global Navigation Satellite System data, which measures actual ground displacement in real time. Unlike seismometers, Global Navigation Satellite System sensors can distinguish between a magnitude 7 and a magnitude 9 because they track how far the ground physically moves, not just how fast it vibrates. Robert DeGroot, Shake Alert Operations Team Lead, stated that this upgrade allows the system to determine earthquake size sooner, which translates to faster alerts. This is not a routine improvement. This is the kind of upgrade you make when you are preparing for a class of earthquake that your existing system was not fully equipped to handle. And Cascadia is not the only source of concern on the West Coast. The southern segment of the San Andreas Fault has not produced a major rupture since 1857. Geological evidence shows that large earthquakes on this section recur every 130 to 160 years. At 169 years and counting, it is past the upper end of that interval. The United States Geological Survey shakeout scenario models a magnitude 7.8 rupture along the southernmost San Andreas and estimates over 1,800 deaths, 50,000 injuries, and $200 billion in damage. Meanwhile, the Hayward Fault, a 74-mile segment of the San Andreas system running directly through the San Francisco Bay Area and its 7 million residents, is independently overdue for a magnitude 6.8 or greater event. A study published in spring 2026 mapped the potential impacts, and the results were described in careful, clinical language that did little to soften their weight. 2 fault systems, both overdue, both in the most densely populated seismic zones in North America, and behind the scenes, both receiving increased monitoring attention simultaneously. Both fault systems are being watched more closely than at any point in recent memory. But what is unfolding along the Pacific coast does not exist in isolation. The broader seismic picture in 2026 adds a layer of context that is difficult to dismiss as coincidence, even if no one is claiming a direct connection. In the first 4 months of this year alone, the planet has recorded 5 earthquakes of magnitude 7.0 or greater. A magnitude 7.5 event struck offshore Tonga in late March at a depth of nearly 230 kilometers. 1 day later, a 7.3 hit offshore Vanuatu at 121 kilometers depth. On April 1st, a 7.4 struck offshore North Maluku in Indonesia at 35 kilometers, shallow enough to generate strong shaking across the region. And on April 20th, a 7.4 earthquake struck off the coast of Iwate, Japan, in what seismologists are calling the 2026 Sanriku event, at a depth of 35 kilometers. All four events occurred along the western and southwestern margins of the Pacific Plate. Different subduction zones, different geological settings, but all part of the same tectonic ring. Correlation does not mean causation. This point must be stated clearly, and it applies here without exception. There is no demonstrated mechanism by which an earthquake in Tonga can trigger a rupture in Cascadia. The distances are too vast, the fault systems too independent. But what seismologists do track is the overall state of stress transfer across plate boundaries. And when multiple segments of the Pacific Ring of Fire show elevated activity within a compressed time frame, it raises a statistical question worth asking. Is the background rate of large earthquakes in 2026 within normal bounds, or is it trending above the mean? The answer, as of early June, is ambiguous. The total number of earthquakes worldwide in 2026 is running close to the annual average, but the clustering of events above magnitude 7 in the first quarter is above the typical pace. Whether that clustering holds or reverts to the mean over the remaining months will be something to watch. Meanwhile, a different kind of seismic activity has been drawing attention inside the United States. The Delaware Basin region of West Texas and southeastern New Mexico has become one of the most active seismic zones in the continental United States, not from natural tectonic processes, but from hydraulic fracturing and wastewater disposal injection. In May 2026, the United States Geological Survey published new research on rapid characterization of earthquake sources in the region, acknowledging that the volume of induced seismicity now requires the same analytical tools used for natural fault zones. This is a separate phenomenon from tectonic plate boundary stress, but it carries its own implications for infrastructure and public perception of earthquake risk. And then there is the quiet detail that went largely unnoticed. In December 2025, the Shake Alert system issued a false alert for a magnitude 5.9 earthquake near Carson City, Nevada. The United States Geological Survey published an update in January 2026 acknowledging the error. False alerts are rare in the Shake Alert system. When they happen, they are investigated thoroughly, not because the system failed catastrophically, but because in a region preparing for a real magnitude 9, even a false 5.9 is a stress test of public response. A false alert tests public readiness for a few minutes. What is happening across the scientific and institutional landscape suggests a preparation cycle that has been building for years and is now accelerating. Consider the sequence. In 2023, the National Science Foundation allocates $10.6 million specifically to build a real-time underwater observatory on the Cascadia Fault. In 2024, Shake Alert integrates satellite-based ground displacement sensors to improve magnitude accuracy for the largest earthquakes. In February 2026, the first offshore strain study reveals that the fault is more structurally variable than models assumed. In March 2026, a plate tear is mapped off Vancouver Island, forcing a reassessment of how the subduction zone is segmented. That same month, Congress is asked for $32.6 million to sustain and expand the early warning system. Each of these actions, taken alone, is a reasonable step in the normal course of seismological research and emergency management. Taken together, they form a trajectory. And the trajectory points in one direction, toward a system that is being instrumented, funded, and upgraded as though the people responsible for monitoring it believe the window of relative safety is narrowing. No official statement says this, no agency has issued a warning, the language remains measured, probabilities, not predictions. But language is one thing, budget allocations are another. You do not spend tens of millions of dollars building seafloor observatories for a fault you believe will remain quiet for another century. There is a concept in emergency management called quiet mobilization. It describes the phase when institutions begin positioning resources, refining response plans, and upgrading monitoring capabilities without triggering public alarm. It is not secrecy. It is sequencing. You build the infrastructure first, you test the systems, you train the responders, and only then do you communicate the risk at a scale the public can absorb. The question is whether the current phase of investment and research around Cascadia and the broader West Coast seismic network represents routine science or the early stages of quiet mobilization for a scenario that has moved from theoretical to operationally relevant. The University of Washington study from February 2026 offers a detail that may be the most consequential of all. Their data showed that faults running perpendicular to the subduction zone may function as fluid conduits, releasing trapped pressure from subducted rock. Co-author Maureen Denol, an associate professor of Earth and Space Science, noted that during a megathrust rupture, one of the primary mechanisms of earthquake propagation is fluid pressure. If some segments of the fault have natural pressure release pathways and others do not, the behavior of a future earthquake becomes harder to predict, not easier. Some sections might slip gradually. Others might remain locked until they fail catastrophically. The same fault could produce radically different outcomes depending on which segment ruptures first and how the rupture interacts with these fluid pathways. This is not a simplification of the risk. It is a complication. And complications, in seismology, are the things that turn models into approximations and approximations into surprises. When models become approximations, the responsible move is to step back and look at the map from a distance. Not to predict, not to reassure, to see the shape of what is actually in front of us. Here is what we know as of June 2026. The Cascadia subduction zone has accumulated over 3 centuries of strain energy along a fault that, when it last ruptured, generated one of the most powerful earthquakes in the geological record of North America. The plate beneath it is not a single intact slab. It is fragmenting, tearing along a newly documented rift off Vancouver Island that reshapes our understanding of how subduction zones behave in their late stages. The fault interface itself is not uniformly locked. Different segments show different coupling strengths, different fluid dynamics, different potential responses to stress. And the first instruments capable of monitoring these processes in real time are only now being lowered to the seafloor, after decades in which the most critical section of the fault existed in an observational blind spot. Simultaneously, 2 major fault systems in California, the Southern San Andreas and the Hayward Fault, are both past their historical recurrence intervals for significant earthquakes. The San Andreas has been accumulating stress for 169 years, against an average cycle of 130 to 160. The Hayward Fault, threading through one of the most densely populated urban corridors on the continent, carries its own independent overdue status. Neither has a predictable timeline. Both have active research programs generating data that suggests the stress levels are real and measurable. Behind all of this, the institutional response has shifted, not in rhetoric, in infrastructure. Underwater observatories, satellite-integrated early warning systems, congressional funding requests scaled to operational urgency. The people whose careers are built on monitoring these systems are building new tools at a pace that exceeds routine. They are not sounding alarms, because that is not how seismology works. But they are building the capacity to detect, measure, and respond to an event that their own probabilistic models say has a meaningful chance of occurring within a generation. The global seismic backdrop adds texture without adding certainty. 5 earthquakes above magnitude 7 in 4 months along the Pacific Ring of Fire. A surge of induced seismicity in the American interior. A false alert in Nevada that tested a system designed for something far larger. None of these are causal links to Cascadia or the San Andreas. All of them are data points that, together, describe a planet whose seismic systems are active, variable, and in some cases behaving in ways that challenge the models built to explain them. There is a phrase that recurs in the seismological literature, almost like a quiet refrain. The absence of earthquakes is not the absence of risk. Cascadia's silence is not peace, it is pressure. And the instruments now being deployed to listen to it are there because the people who understand it best are no longer comfortable with not hearing what it has to say. The instruments are descending to the seafloor. And for the first time in the history of Cascadia observation, there will be ears pressed directly against the fault. But listening and understanding are not the same thing. The data that begins flowing from those titanium-encased seismometers and millimeter precision pressure gauges will enter a scientific landscape that has just been forced to redraw its own assumptions. The fault is segmented. The plate is tearing. The fluid dynamics beneath the locked zone are variable and poorly mapped. Every new data set from the COSZO observatory will be interpreted against models that their own creators now acknowledge are incomplete. This is not a failure of science. It is the nature of studying a system that operates on timescales measured in centuries, while human observation windows are measured in years. The question that no agency will answer directly, because no agency can, is a simple one. How much warning will there be? The 2004 Sumatra earthquake, the last full margin subduction zone rupture to occur in the modern era, provided essentially no precursory signal that instruments detected before the fault moved. Magnitude 9.1. Over 200,000 lives lost. The plate had been locked, quiet, and then it was not. The Tohoku earthquake in Japan in 2011 followed a similar pattern, a magnitude 9 that exceeded every hazard estimate for that section of the trench. The warning came not before the earthquake, but after it started, in the seconds provided by early warning systems for those inland to brace. This is the operational reality that Shake Alert is being upgraded to handle, not prediction, detection. The difference between those two words is the difference between preventing a disaster and surviving one. For Cascadia, the current best-case scenario is not that someone will forecast the earthquake days or weeks in advance. The sensors will catch the first P wave as it radiates from the rupture. The algorithms will calculate magnitude and location within seconds, and the alerts will reach Portland, Seattle, and Vancouver before the S waves arrive with the destructive shaking. Minutes at most, possibly less. 13 meters of accumulated displacement, a fault that stretches from California to Canada, a plate that is breaking apart beneath the ocean floor, and a monitoring network that is, only now, being built to match the scale of the problem it is meant to observe. No one is predicting that an earthquake will happen tomorrow. The data does not support that claim, and no credible scientist would make it. But the data does support something else, something that carries its own weight. The people who study this fault, who spend their careers measuring its silence, are building instruments faster than they have at any point in the last 50 years. They are doing it with public money, institutional backing, and a sense of priority that is visible in engineering, even if it is absent from the headlines. On the seafloor off the Pacific Northwest, the sensors are settling into position. The cables are live. The data is beginning to flow. And Cascadia, for now, is still quiet.